Hello, this is Raf Alvarado and welcome to Exploratory Text Analytics. In this video, we're going to look broadly at the concept of classification. So in this course, we've been looking mainly at unsupervised methods. It's one of the premises of the course that I began with. But in our final class, we're actually going to look a little bit at classification and kind of about the relationship between the two methods within machine learning of supervised and unsupervised methods. So here I have a broad diagram showing the place of supervised and unsupervised methods within the general category of machine learning, which is in turn part of artificial intelligence. Of course, supervised and unsupervised methods are sometimes seen as synonyms for the idea of classification being supervised and clustering being unsupervised. In this diagram, there's a little bit of liberty being taken here of things being spread out into different places. We have deep learning as a different category, and in fact, that might be seen as a kind of supervised learning. But I just want you to get a sense of how these are different areas within this broad field of artificial intelligence. We're going to look specifically at document classification and see how that relates to the general topic. So here's another view of, I think, a better view of how they are related, or how they are distinguished, rather. Classical machine learning is divided into supervised and unsupervised methods. And within the supervised method, you have classification, where you're trying to identify a label for a set of input variables. You have regression, which is what you use when you're dealing with continuous data. Then you have unsupervised methods. We've looked a lot about those already. Interestingly, here we have association as one of the unsupervised methods, which is actually kind of nice because it really is a whole approach, if you will, within unsupervised methods that's quite distinct from just simple clustering. Yet again, we have here another diagram just to reinforce the idea of the broad field of machine learning. We have, unsupervised and unsupervised, the classical stuff over there, but there are all these other things too. Reinforcement learning, ensemble methods, neural nets, and deep learning are pulled out here as a distinct domain, whereas again, they might be considered to be part of supervised, but we can, chop this up in lots of different ways, just showing you different ways in which the world can be chopped up in this space, and to, get a sense that we're kind of moving out beyond the narrow confines of just clustering to this broader area. All right, so let's look at classification more specifically. It refers to the task of predicting the category of a thing when the use of the category on similar things is known. Categories are also called classes, labels, annotations, and we call this this prediction when the system you've created, the program you've created, is able to learn the principle, and I'm being vague there because there are different ways that principle can be represented, but learning the principle that governs the application of the label by humans. So the basic idea is that, everybody understands this general classification task, say, for example, of spam detection with documents, or maybe trying to detect the presence of a cat in an image. Obviously, there are much more sophisticated tasks of trying to detect the presence of a particular person in an image, face recognition, and so forth. But the basic idea in all these cases, from simple to complex, is that you have a data set, a whole bunch of observations with features, and one of those features is a label, some identifying label that you'd like to predict from all the other features. And those other features could be properties of the image, or it could be properties of the text. It could be metadata associated with the images and or text, but that's the basic idea. Now, we're used to doing this kind of task these days using tools like neural networks, but there's a long history to approaching this problem using different methods. Traditional artificial intelligence sought to develop an approach that was much more deductive, using a system of rules where the AI, as it were, would have encyclopedic knowledge of the world and would be able to draw inferences mechanically from this knowledge of the world when combined with perception of the outside world, the perception of an image, say. This is what I call the ancient dream of logic, where you have this whole system that is able to, on its own, make inferences and observations about the world. But machine learning is a method that emerged a little later in the history of AI, a sort of more probabilistic approach, and became dominant in the 80s. It uses a more what we might call brute force method to learn rules statistically about the world without having so much of an internal model of the world against which to compare things. It's more of an inductive approach. So we all know now that this approach has been extremely successful since the 90s, and with the rise of the web and with Google, we see that these methods are extremely powerful, and they're the reason why data science is on the map, really, in many respects, is because of the success of the machine learning approach to this problem of classification. Now, one of the problems with this approach is that we produce these models. Like if you look at a neural network as a way of representing the world, to come up with a prediction, it's very hard to figure out why a neural network makes a decision about a cat being in a picture or not. This is known as the problem of representational opacity within sort of a philosophical view of it. A contrary view is to try to produce something called interpretable AI in order to overcome this problem. But the basic idea is that you have this opposition between interpretability and predictability. So when we say interpretable, we mean like your model that you use to make the decision is very parsimonious. It's got a few input features. Here we say 2 or 3 to visualize them. The features tend to be intuitive. You sort of understand what they are. They're not these vague features like in word embedding. You don't know what those features actually stand for. And the process to generate the results is understandable. For example, a decision tree is classically viewed as more intelligible and interpretable than a neural network. So that's what we mean by interpretable. So regarding the concept of inference that we keep referring to, just as a side note, induction means learning a rule from a model, a rule or model from data, and then applying that rule or model to other data. So you see a lot of examples, lots and lots and lots of examples. You generalize in some way to make something that you're going to call a model, and then you apply that model to other instances and make your decision that way. And that's where machine learning. That's the space within which machine learning, as we're considering it here, operates. Deduction is working within rules alone, sort of within using theorems. There are many forms of inference. There's abduction, for example. Inference and prediction are often contrasted. And one way in which they are contrasted is that inference is usually associated with a scientific effort to understand the world. So, if I'm going to build a model, learn it from the data empirically, that model is going to, in some sense, be a picture of the world, or something that stands on its own as an intellectual contribution to knowledge and to our understanding of the world. Whereas prediction is more about just providing an answer that will drive decision making. Should this patient be subject to a regime of drugs based on our prediction that the patient has a certain disease. So it's really about orienting you to acting in the world, whether or not the picture of the world that was used or the model of the world that was used to come to that decision makes sense. All that you have is the track record, if you will. So a more formal definition of classification is that typically you have these two things. You have a vector of labels, and when you're thinking about data frames, think of that vector as one of the columns, maybe the last column. It's the thing you're trying to predict. It's the label. It's often called the ground truth. And then you have the matrix of feature vectors, which is the rest of the data frame, which is the actual information that you have available to you. Each vector element, is a member of a domain or column. Some domain, associated with, say, a measurement of some kind or some other metadata feature that you're dealing with. Y hat is the symbol for the guessed or predicted value of y. So in these cases, what you're doing in prediction is, you know, as we're going to see, you train your classifier to use the data in X to predict Y, and so you specify a Y as a prediction, and then you compare Y hat to Y. There are many synonyms for X and Y. You'll hear people, and this kind of varies from the domain they come from. You'll hear treatment and response variables, features and labels, sometimes if you're ambitious, cause and effect, predictor variables and outcome, and so forth. There are actually quite a few terms that you'll see used for these things. These are represented in a data frame where every observation is a member of X, and here we have lowercase x, I1, I2 to ij. Just imagine this is essentially a row in a database, in a data frame. So for document classification, we map these terms in the following way. So X is usually called D for a document, and Y is called C for the class of the document. So the classes come from a finite set. Sometimes it's a small set like spam or not spam. Sometimes it's a long set, such as the subject matter of a text may be a classification set. Whether like the genre, for example, whether it's a text is fiction or nonfiction, or whether the text is suspense or romance or whatever. Those things belong to the set C. And M usually stands for your set of labeled documents. So your labeled documents will be where you have a co-occurrence distribution of documents and categories or classes. And these are what you're going to use to train your model. V is often used for the vocabulary of terms that are used in the documents. And although W, the lowercase w, is often used for the word instance, i.e. the token, word, just don't get confused by the idea that word has an ambiguous meaning. Sometimes in common usage it refers to what we've been calling terms or unique vocabulary elements, and sometimes it seems to refer to specific instances, and in this case it does refer to specific instances. In addition, the position of the token is referenced by the suffix I, as in WI. So some classification tasks that you're probably familiar with: spam detection, language identification, subject grouping, genre detection, author attribution. We're looking at some examples in this module where digital humanists have applied them to some very interesting tasks of exploring different kinds of text. In one case, we're looking at dream reports. In another case, we're looking at different kinds of content within different genres of writing. Emily Dickinson's poetry, for example, and American fiction. And those essays we will talk about later. So some of the standard classifiers that are used for document classification, these are ones that you'll see in other contexts as well: linear regression, logistic regression, support vector machines, decision trees and random forests, even neural networks. In the essays that we're reading, we're going to look at support vector machines and naive Bayes, and we're going to drill down on naive Bayes and actually implement a classifier in our code walkthrough using naive Bayes. Here's a simple machine learning pipeline that you all are probably familiar with, coming from taking having taken classes in text mining and machine learning. Basically, you've got your data sets, your data retrieval, which we know all about in the area of text analytics, and we prepare these things. We establish the text, as we've talked about, creating a digital analytical edition. We may do some feature scaling and selection like PCA and so forth, and then we apply different models using different machine learning algorithms to that data, and we test these models to see whether they perform the tasks that we have before them well. And then we iterate, we mess with parameters and things like that until we get to where we want to go, and then we can actually deploy our classifier. So this is a lot different. This is everybody understands this workflow, but I put it here just to highlight the difference between what we have been doing just exploratory text analytics, we typically, it's more of that loop of reiterate till satisfactory model performance. Usually that model evaluation and training in exploratory stuff is a human being interpreting the results, making sense of them. Whereas here it's very precise in the sense of the results are pretty much going to be this comparison of a predicted label with an actual label. And it changes everything with respect to what one means by performance. The closest thing to this we've seen so far in the exploratory space has been the use of Perplexity to compare language models, but this is much more precise. Some of the things that affect this pipeline specifically within the area of text analytics, in the area of text data preparation, which we've already talked about, is that we convert our source data into analytical format of features and response variables. So we add a response variable to what we've already have in our typical data model, and everything we've learned already up to this point applies to the preparation of the data for this purpose. We also, in the area of modeling, we pick classifiers and algorithms that are tuned to working with text. And oftentimes we split things into training, testing, and held out dev tests. So this is talked about in the reading that I had you look at. Finally, for performance and evaluation, within text analytics, we tend to look more specifically at recall and precision and F-score. There are other concepts as well that we can look at. And actually, I have a presentation of all the different ways of all the different performance metrics like sensitivity and so forth, and recall, precision, accuracy, and sort of relating them all to each other so that you get a grasp of how they all relate to each other, because they are often mentioned in a kind of, I feel like, a non-systematic way, and also affecting one's understanding of these things is the fact that some domains talk about them differently than others. So for example, if you're coming from medicine, you're going to talk about these things slightly differently than if you're coming from text analytics. But in fact, there's a unified way to look at performance and evaluation, thinking in terms of conditional probability, and I'll present that to you later. Significance testing within text analytics, we don't usually use statistical methods such as p-values because performance test results are non-Gaussian according to Jurafsky and Martin. Also, we tend to use non-parametric methods such as bootstrapping for significance testing. In addition, as we've seen throughout this course, the interpretation of results never quite goes away. There's always the application of domain knowledge and user feedback to the fine-tuning of performance, in addition to the methods that the more precise methods that we're going to talk about. So let's look at the document classification problem itself. In general, the problem can be seen as one of Bayesian inference, and this is actually similar to what we saw earlier when we were looking at natural language processing and the coding problem of trying to infer, say, a part of speech tag for a word. It's precisely the same problem, actually. The approach that we took earlier, though, was what was called a decoding problem. It wasn't technically a decoding solution. It wasn't a learning solution in the sense that the decoding just happens once. You just make a guess, you decode, but you don't actually iterate and improve your model through the comparison of the ground truth to the truth. Here you do, and that's what makes a learning. That's what makes machine learning. The fact that you actually iterate and get closer and closer to some convergent solution. So anyway, you're trying to predict the class given the document. That is, for any document, what class are we talking about? What is a proper category for that document? And we use a technique called maximum a posteriori value. You just get the argmax of the category that predicts the document best. So you use every model, every category gets a model, and essentially it's like a language model that we've already seen. And for every one of those models, you apply the document to it, and the model that produces the highest score predicts that document with the highest value is considered to be the category. And the naive Bayes approach builds on this method. You can think of naive Bayes as essentially building on the language model approach that we already looked at, where you're predicting the likelihood of a sentence with your model. Here you're doing it in a systematic way so that every category gets its model, and then you just pick the one that works, that has the highest value.